transfer functions. We considered all possible cases: symmetrical, asymmetrical, even length, odd length, and then we started discussing general FIR nonlinear phase filter with the highest coefficient equal to highest power coefficient equal to 1, plus 1 or minus 1. Because Km is equal to plus 1 or minus 1, it creates a problem in going to the next stage, and we had taken just one example. But before that, one of the mistakes that I have made in the paper is I have mentioned a single multiplier FIR lattice, which incidentally does not exist so far. Unless you find one by the end of this course, it shall remain an open problem in future also. A single multiplier FIR lattice section. IIR it exists, for FIR it does not. Okay. So, you can make your effort and make an original contribution to literature if you find one. All right. Single multiplier, single delay. Now, to continue with the problems, first we had considered last time length, odd length and symmetrical filter, that is 1 plus H1 Z inverse plus H2 Z to the minus 2 plus H3 Z to the minus 3 plus Z to the minus 4, odd length and symmetrical. And we had said the decomposition would be 1 plus H1 Z inverse, not H1, H3 Z inverse, we take this one, plus H2 Z to the minus 2 plus H3 Z to the minus 3 plus Z to the minus 4. In other words, we extract a linear phase in a particular fashion, that is, we use the higher power coefficient for symmetry. I could have used H1 here, and then I had to subtract an H3 minus H1 times Z to the minus 3. In other words, the tap had to be after 3 delays, but then after 3 delays calculation becomes a little bit more involved, and therefore to reduce the calculational effort we bring the higher power coefficient here. Do you understand the difference? It will work in both cases. No increase in complexity, no increase in number of multipliers, but to find that coefficient would be a little problem. It is much easier here. Then we have to subtract, we have to use H1 minus H3 Z inverse. So, the the structure would be like this: X, then Z inverse, you have two summers, K1, K1, the next one would be a box K2, the next one K3 would be, because our decomposition would be here from H5, from H4 we will go directly to H2, but there is a problem. This is not the middle term, this is the middle term, but it has to be broken into two parts, that is, you have to write this as H2 by 2 plus here also H2 by 2 Z to the minus 2, right. Okay. This we have already illustrated, and therefore K2, the next one would be K3 would be equal to 0. So, simply a Z inverse, and finally a K5, K4 equal to 1. The output of this now has to be added so that this term is also accounted for. But while going, can't we see that K2 shall be equal to H2 by 2, because our decomposition is this. So, K2 is H2 by 2, and K1 also we know, K1 is H3, that is why I asked you the question. There will be 1 plus H2 by 2. Then you see we take a tap from here, because we simply have to get H1 minus H3 Z inverse. If we had taken a tap from here, that is after 3 delays, then we had to calculate what signal is here, and that requires a crisscross. You will have to calculate all the contributions. Do you understand the problem? Yes. But taking a tap from here does not create a problem. So, we simply multiply it by H1 minus H3 and then add the 2 signals. This is my output. Okay, it is taken care of. Let us consider the same case with a negative power. Okay. The next example, we take the same case H4 of Z, that is odd length and asymmetrical coefficients, not asymmetrical coefficients, it is not linear phase. Coefficient of the highest power term, coefficient of Z to the minus 4 is equal to minus 1 instead of plus 1. Then we shall have to bring in asymmetry, okay, to decompose into linear phase plus some other transfer function. We shall have to bring asymmetry. So, let us say 1 plus H1 Z inverse plus H2 Z to the minus 2 plus H3 Z to the minus 3 minus Z to the minus 4. To decompose this, we have to write like this: 1 minus Z to the minus 4. Since these are asymmetrical, antisymmetrical, we have to make all of them antisymmetrical, and therefore, we have to make minus H3 Z inverse. I have plus H3 Z inverse. Okay. Right? Now, what do I do with H2? If the filter is antisymmetrical, then the middle coefficient must be 0. So, that is it. That is the linear phase. Do you understand this? Every case has its own peculiarity and distinctiveness. So, the terms that we have to add now is H2 Z to the minus 2 plus, pardon me, H3 plus H1. I have to restore to the original value. This H3 must go and H1 must come. So, Z inverse. This is the term that we have to add. This is no longer a linear phase term. It is not linear phase. This is linear phase. Now, as far as realization is concerned, I now require 2 delays, 2 tappings, one after Z inverse and the other after Z to the minus 2. Let us see the realization of this. I have X, let me draw it on a different page. I have X, then a Z inverse, two summers, K1, K1, now I must what do I have next? In the decomposition from H4 we suddenly drop to H1. So, K2 equal to K3 equal to 0. You see the simplification? So, we shall have 2 delays here. K2 is 0, K3 is 0, 2 delays, and then finally we shall have K4 equal to minus 1. Do I know K1? Minus H3, that is correct, minus H3, wonderful. So everything is done except that we have to take now 2 tappings. You see, we have synthesized the linear phase transfer function by observation, because from 4 it has dropped to 1 because of the anti-symmetry. If it was symmetry, then from 4 it comes to 2. Okay. So I have to use 2 taps. Let us say this is alpha and another here, okay, z to the minus 2. Let us say this is beta, and add with this. The only thing that remains to be found are the values of alpha and beta. Now, what comes here? What is the signal here? Alpha z inverse, right, plus beta z inverse, from here to here is beta z inverse. Now, what is the signal here?
K1 plus Z inverse into X.
K1, I beg your pardon, K1 plus Z inverse. That is right. That is the transfer function, K1 plus Z inverse. Agreed? This should be equal to H2 z to the minus 2 plus H3 plus H1 Z inverse. Agreed? Now match the coefficients, and obviously beta should be equal to H2. That is right. Beta is equal to H2, and alpha should be equal to H3 plus H1 minus H2 K1. And what is K1?
Minus H3.
So it would be plus H3. These values are given wrongly in the paper. Okay. Any question on this? Let us take the other 2 cases. Next case, even length and highest power coefficient equal to plus 1. So even length, let us take a 5th order, H5z equal to 1 plus H1z inverse plus H2 z to the minus 2 plus H3 z to the minus 3, H4 z to the minus 4 plus z to the minus 5. Coefficient is 1. And the decomposition now would be 1 plus H, what?
1 plus H4.
H4 z inverse. This has to couple with this, plus H3 z to the minus 2 plus H3 z to the minus 2 plus H4 z to the minus 4 plus z to the minus 5 plus, yes, H1 minus H4 z inverse plus H2 minus H3 z to the minus 2. Okay. Now, the first one is linear phase, and I can synthesize it in the usual manner. What shall I have? I shall have X Z inverse I have to show the Z inverses explicitly because I want to take the taps. I can't show it as boxes. Okay. I would have been very happy if it was so. K1, K1, and since you are a little more experienced than you were earlier, you should now be able to tell me what is K1. K1, H4 divided by 1 plus H3, that is correct. Okay. The next one is Z inverse. Unfortunately, I have to draw this Z inverse also, and then K2 and K2. I also know what is K2. K2 is equal to H3. All right. Then what are the next two? Next two are K3 and K4 are 0, and therefore I shall have two delays. I shall have two delays, Z inverse, and finally K5 equal to plus 1. K5 equal to 1. The output shall combine with taps from Z inverse, that is from here call this alpha, and from here call this beta. Okay, because I have Z inverse and Z to the minus 2, and if you follow the same procedure, can I leave the algebra to you? If you follow the same procedure, you get beta equal to H2 minus H3 and alpha equal to H1 minus H4 minus H2 minus H3 multiplied by H4 divided by 1 plus H3. Do you see what this is? This is beta and this is K1. That is what we had to produce, H1 minus H4 we had to produce, and the left hand side was alpha plus beta K1. So, that is it. These numbers are also given wrongly in the paper. Please do make correction. Finally, the case of even length and coefficient of highest power term equal to minus 1. So, we have to go for anti-symmetry. H5Z equals to 1 plus H1 Z inverse plus H2 Z to the minus 2, H3 Z to the minus 3, H4 Z to the minus 4 minus Z to the minus 5. And the decomposition now would be 1 minus H4 Z to the minus 4 minus Z to the minus 1, that is right. Then next term H3 Z to the minus 2 plus H3 Z to the minus 3 plus H4 Z to the minus 4 minus Z to the minus 5. Then you have to add H4 plus H1 Z inverse plus H2 plus H3 Z to the minus 2, and I think you can do the rest. The only thing that I want to point out here is K2 is equal to minus H3, agree? K1 would be equal to minus H3 divided by 1 minus H4 divided by, that is correct. Let me correct it, minus H4 divided by 1 minus H3. K3 and K4 shall be equal to 0 and K5 would be equal to minus 1. The values of alpha and beta, I have done the rest. Beta is H2 minus H2 plus H3. Beta has to be H2 plus H3 because beta Z to the power minus 2, and alpha equals to H1 plus H4 minus beta K1. So, beta is H2 plus H3 and K1 is H4 divided by 1 minus H3. I have changed the sign. With a little bit of maturity, you will not have to do the intermediate steps in algebra. You can write these things directly. Okay? So, either the highest power coefficient plus 1 or minus 1 actually is a welcome step because it reduces your effort. All right. If it is linear phase, that also reduces the effort considerably. If it is not linear phase, neither is the coefficient of the highest power term equal to plus 1 or minus 1. Even then, with a little bit of ingenuity, you can apply some of this simplification. Suppose you have h5 z to the minus 5. Take 1 there, all right. Then the rest you can tap it out. Only thing is, you shall have to use a little more calculational effort and perhaps one more multiplier. Okay? But that may be compensated by the reduced number of multipliers in the linear phase term. Do you understand? You see, if it is general h5 plus h5 z to the minus 5 or minus h5, you make that h5 1 and bring it out so that the transfer function remains intact. If you can decompose into linear phase and nonlinear phase, the linear phase term reduces the number of multipliers, and therefore your number of multipliers may remain the same as the number that you will require if you synthesize this directly, okay, as a general FIR transfer function. So, bringing in linear phase or highest power coefficient equal to plus 1 or minus 1 is an advisable step for a practical FIR design engineer. And with that, we close our discussion on FIR, on realization of digital filters. We next go to the most important topic, that is digital filter design. All this that we have been doing ultimately should end up here. That is the problem that you shall have to handle in practice, digital filter design. We have already done some examples. We have done first order low pass, first order high pass, then second order is the minimum order for band pass, band stop. Given a problem, we should be able to solve it even without sophisticated digital filter design techniques. But if the specifications are very tight, let us say delta P is of the order of, let us say, 0.1 dB and delta S is, let us say, 120 dB. The order has to be high, and it may not be possible to do it by cascading on the second order by trial and error. You shall have to know what the order is and how to go about it. Okay? But given a practical situation, most of the practical engineers, what they do is they use synthesis by analysis. That is, they cascade some second order term, find out does it do the job, use a MATLAB to find out the performance. It does not, so change this, change that, trial and error, but not people who are trained in IIT. They do it in a sophisticated manner, systematically, and they say with confidence, this is the optimum. You can't do better than this. Okay? You can't do better than an IIT student. Okay? Right. So, the problem is that specifications are given, and these specifications are, as you are already aware, the tolerance in the pass band, tolerance in the stop band, and the band edges. Okay? Now, if it is a simple low pass filter, then you know delta P, delta S, omega P, omega S. I beg your pardon, these are digital filter specs. So, small omega P, small omega S. On the other hand, if it is a band stop filter, then you require omega P1, omega P2, or the bandwidth and the center frequency, and also omega S1 and omega S2. So, I will say omega P omega S as a vector. Okay. Delta P delta S may also differ from one stop band to another stop band. All right. So, these are in general the specs. You can have multi band pass or multi band stop or a combination filter, low pass plus something else. From the specifications, then your job is to find out a transfer function h of z. The specifications we are talking about are magnitude specs. Usually we don't design digital filters to satisfy phase specifications, although there are situations where this is to be done. But for phase, you know what our aim is, what is our objective in digital filter design as regards phase is concerned. Phase should be linear. We can't obtain this with an IIR filter, we can obtain this exactly with FIR. So, phase goes out of consideration. In IIR, phase is a consideration, but usually we don't design it that way. We design for satisfying the magnitude specs, and then whatever phase comes we accept it and then try to compensate for the non-linearity of phase by cascading all pass filters. Okay? All pass filters are there for everywhere. Whichever way you want to go, all pass filters shall accompany you, whether you like it or not. Okay? So, the transfer function has to be found, and then once you obtain an h of z, then with the knowledge that you have already acquired, you realize, then you go either to software, write a program with a dedicated PC, or use a programmable chip and program it, or make ab initio hardware realization. If it is simple enough or a most complicated, it is either extreme. If it is very simple or very complicated, then you design your own chip and fabricate it. If it is in between, then you try to use one of the TI or AD or some other chip, AT&T. Now, IIR and FIR design, they follow entirely different routes, and they are very different from each other. IIR design usually can be made with a degree of confidence, FIR no. Although FIR is advantageous from linear phase considerations and also stability considerations, FIR filters are unconditionally stable. With IIR there is a problem, you have to check the stability at some point of time. But the advantage of IIR is that you can use much lower orders, that is the hardware complexity or the software complexity is much lower than that of the corresponding FIR filter. And the other advantage is that IIR filters usually can be designed analytically to the given specifications, to satisfy the specifications exactly, except for word length errors, that is except for the errors arising out of using a finite number of bits. Okay? So, IIR filters can be designed analytically, FIR filters can also be designed analytically, but the level of confidence is much lower. The filter that you design may or may not satisfy the specs, and what you have to do is, after you complete the design in FIR, you have to actually calculate, compute its performance, find out if it satisfies the specs. If it does not, then you go back and change. So, it is an iterative process, whereas in FIR it is one step process, and this comes about because IIR specs can be transformed to an analog filter specs. okay, can be transformed to analog filter specs by using a transformation from omega, normalized digital frequency, to analog frequency capital omega. Use a transformation from the digital normalized digital domain small omega to the analog frequency domain capital omega, then you get the corresponding analog filter specs. From the analog filter specs, you can, by the approximation techniques, you can design a given a particular analog filter to satisfy these specs, and this is normally done by transforming the analog filter to a normalized analog low pass filter, and then using the transformation back. So, you design an HA of S and then go apply another transformation to go from small s to the Z domain, okay, from small s to the Z domain to obtain an H of Z. This is the route that is followed for IIR, analytical digital filter design. One might ask, in this age of computers, when very large capability computers are available, why should we go through this analytical technique at all? Why can't you use a very blind approach? Like the specs are given, you estimate an order. Let us say from the given specs I estimate that a 10th order IIR filter should do. Then I require 20 unknown constants, 10 in the numerator and 10 in the denominator, of which the number can be reduced by 1. In the denominator, the constant can be written as, so 19 coefficients, all right. I guess these coefficients, I start with an initial value and I put it to the MATLAB, find out what the results are. Well, obviously, since it is a blind guess, so many blindnesses combined, okay, the order we didn't know these 19 coefficients, we just assume some, it does not satisfy, all right, change, and then go on doing this. It's a madhouse. I mean, you never know whether you will converge or diverge. In the initial stages of development of digital filters, the Bell Lab engineers, Rabinowitz, Oppenheim, Schaeffer and others, very famous names, Gold, Rader, R-A-D-E-R, they did exactly the same. They went through blind designs. However, at the present time, sophisticated computer programs are available for digital filter design, IIR or FIR. Now, companies do use them. They are very costly programs because they have been derived by putting many thousands of man hours, and they are usually proprietary for a company. They do not divulge it to others. There are some open programs available on the internet which you will have to modify to suit your designs. But then if you can design it analytically, nothing like it, because there is a measure of confidence which cannot be matched by any other filter design. The people in industry argue, the software program owners, they argue that for an engineer something which works is good enough. Why bother about analytical design and things like that? Well, we do not view this very favorably in the academic community, and people with graduating with an IIT degree, well, when they say this is the design, they have to say it with confidence that you cannot do better than this. No computer can do better than this. And fortunately, since analytical designs are available, we shall use computer aided design algorithms only if we have to. Okay. If you do not have that much of man hours at your disposal, that much of computational capability, well, go ahead and use it. Now, let us look at why is it that IIR filters are designed from analog filters. This is also historical, and later on it has been found that the analytical complexity associated with IIR analytical design is so large, so complicated and so involved that a better way is to use our huge storage of knowledge in analog filter design. Analog filter design is an advanced art. Okay? Almost everything is known about analog filters. They usually give rise to closed form expressions. We have illustrated with Butterworth and Chebyshev, very elegant expressions, and you can find out the transfer function exactly. Not only that, for given specs except for elliptic filters, they are tabulated. Handbooks of filter design are available, and therefore you may not have to do the intermediate steps. You may simply consult a handbook. These are the specs and there is a design given. Okay. So, you can take that design, analytical design, then do your transformation, analog filter, then do your transformation from S plane to Z plane, obtain the filter transfer function, realize it, make an analysis with that has to be done with the finite number of bits. How many bits are you using, 8, 16 or 32, make an analysis, find out whether they satisfy or not, and then make incremental adjustments. In analog filters also, LCR filters for example, after putting it on a hardware, you have to check, you have to make an experiment to see if it is satisfied. If not, then you have to tune the filter. So, this is tuning is required because of finite word length requirements. Otherwise, if infinite number of bits were available, your design was perfect. Okay. So, these are the reasons why analog filter form the parent filter for IIR digital filter design. There are various kinds of transformations that are available, and the two transformations that are generally used go by the name of IIT and BLT. IIT stands for impulse invariant transformation. Okay? Impulse invariant transformation. This is very simple conceptually, but has its own disadvantages. Impulse invariant transformation, and BLT is the bilinear transformation. Impulse invariant transformation is conceptually very simple, but is always amenable to aliasing error, aliasing distortion. Aliasing cannot be avoided in impulse invariant transformation, whereas bilinear transformation is free from aliasing error. Okay? Even then, why do we discuss IIT? Because it is very simple conceptually, and the calculations are also much simpler. So, if the distortion can be contained within a reasonable limit, then it does the job. Most of the filters, the IIR filters for biomedical signal processing for example, people do not want to go into the complication of bilinear transformation, they simply use impulse invariant transformation, and they if they work for an engineer, if anything that works is good enough. So, people still use IIT. Some of the Mitra's second edition for example does not discuss IIT at all, he only uses bilinear transformation. That is one reason why I am asking you to take careful notes. Impulse invariant transformation, what one does is one takes a given analog filter obtained in the same manner, that is by using by using some transformation. You transform small omegas to capital omegas. Then you decide on a filter H A of S, an analog filter, all right. Obtain its impulse response, small h a of t, and then sample it, sample the impulse response, that is obtain h a of n t, and call this h of n. Do you see how simple it is? Call this h of n, from h of n take z transform, obtain your h z. So, the relationship between the analog filter and the digital filter, we have derived h z from h a of s. The characteristic is, or the distinctive characteristic is, that the impulse response remains invariant. That is, the digital filter impulse response is the sampled version of the analog filter impulse response, and if sampling theorem has been respected in the process, then there should be a 1-to-1 representation. That is, given h of n, you should be able to construct h a. Given h a, you should of course obtain h of n. This is the problem. This is the problem. This is why aliasing occurs, because no transfer function in practice is band limited. If you want to respect the sampling theorem, the sampling must be such that the sampling frequency is greater than or equal to twice the highest frequency at which h a of s is non-zero. No transfer function can stop abruptly at a particular point, because they would disobey the fundamental Pauli-Wiener criterion. Okay? They would be non-causal also, that is unrealizable. So, the transfer function, no transfer function is band limited, which means that some amount of aliasing distortion is bound to occur. So long as you contain this to within the tolerable limits, it is perfectly all right. So, the procedure is extremely simple. What you do is, suppose h a of s, for simplicity we assume that it has only distinct poles. Let us say I equal to 1 to n a I divided by s minus p I. What happens when I have repeated poles? We will come back to it later. We will discuss later. Suppose we have capital N number of poles in the transfer function. Let all the poles be distinct. P I can be real or can be complex. Okay, but the real part of P I, if it is complex, must be negative. S equal to P I is the pole. Poles must be in the left half plane, left half of the S plane. So, real P I must be negative. Okay. Therefore, H A of t, now I shall write only summation, I will not put the limits, it is implied. H A of t therefore shall be A I e to the power P I t u t. Okay. E to the P I t u t, and if I sample this at intervals of capital T, then obviously what I get is A sub I e to the power P I t to the power n, then u of n t, which is the same as u of n, the digital step function. And I call this, I identify this as my h of n. So, my transfer function becomes h of z equal to summation a sub I divided by, this is alpha to the n. So, 1 minus alpha e to the p I t z inverse, this is the z transform, okay, I equal to 1 to n. You see, from the given transfer function analog, I go to the digital in a very simple manner. What do? I replace 1 by s minus pi by 1 by 1 minus e to the pit z inverse, which means that the pole at s equal to pi is transformed to the pole at z equal to e to the power pit. Now, if this transformation is to work, then a stable analog filter should be transformed to a stable digital filter, right? And you see the transformation that we are using is z equal to e to the power st. When s equal to pi, I get z equal to e to the pit. So, the transformation from the s plane to the z plane is z equal to e to the st, which I can write as e to the sigma t e to the j omega t, right? And therefore, magnitude z is greater than, equal to, or less than 1 for sigma magnitude z. Magnitude of this is 1, so it is simply e to the sigma t. It would be greater than 1 if sigma is greater than 1. It is equal to 1 when sigma, I beg your pardon, 0. Sigma greater than 0. It is 1 when sigma is equal to 0. It is less than 1 if sigma is less than 0, which means that a pole in the left half plane, left half of the s plane, transforms to a pole inside the unit circle. Inside the unit circle, the j omega axis transforms to the unit circle, equality signs, and the right half plane transforms to outside the unit circle, and therefore our first criterion is satisfied, that is, a stable analog filter shall go over to a stable digital filter. Can I repeat this point? You see, when sigma is less than 0, that is, the pole is in the left half plane, then magnitude z is less than 1. Therefore, this transforms to a point inside the unit circle, and therefore, if this is a stable pole, it goes to a stable pole. The j omega axis for which sigma is equal to 0 goes to magnitude z equal to 1, so it goes to the unit circle. And the right half plane, where no poles should be located, goes outside the unit circle. Okay? So, a stable filter goes into a stable filter. The weakness of this transformation is that H A of s may not be band limited. How does it reflect in the transformation? 1 by s minus pi transforms to 1 minus e to the pit z inverse. How does it? Well, a sub I summation goes to summation a sub I. What we are transforming in this are the poles. The pole at s equal to pi, we find the corresponding pole in the z plane. We have no control over the zeros. Agreed? No control over the zeros. The transfer function zeros from the analog plane are not transformed according to this relation. Whatever zeros come, we will have to accept, and this arises because H A of s is not band limited. This is how it is reflected. Since we have no control over the zeros, therefore, the transfer function that we get shall not be exactly what we wanted. And these are two ways of looking at it. One is aliasing point of view, and the other is aliasing occurs because we have no control over the zeros. On the other hand, in bilinear transformation, we transform poles as well as zeros. We transform the total function. This is one of the weaknesses of the impulse invariant transformation. As an example, if I have let us say the normalized first order analog filter, normalized first order analog filter, you call it Butterworth, call it Chebyshev, call it elliptic, it does not matter, first order is first order. This transforms to 1 by 1 minus e to the minus t z inverse, which means if this is written as x z by, I beg your pardon, y z by x z, then y n, the difference equation would be y n equal to x n plus e to the minus t y of n minus 1. This is the first order filter. First order digital filter derived from first order analog filter. There is no order change. First order goes to first order, okay, because the transformation is a linear transformation. Similarly, in bilinear also there is no order change, as you shall see. The $1,000,000 question here is, you have maintained the impulse response invariant. What about other responses? If the impulse response is invariant, let me tell you that if you know the impulse response of a digital system, then you can find the response to any other input by using the convolution theorem. Now here it's not, the situation is not simple. You had an analog filter whose impulse response you have found out, and you have sampled that impulse response to obtain the impulse response of the digital filter. Does it imply that the response of the analog filter to a unit step, the response of the digital filter to a unit digital step, are these sampled versions? That, in other words, is the step response invariant? Impulse response is invariant by design. Is the step response, does the step response remain the same? That is not necessarily. Step invariant transformation is quite different from here. We shall demonstrate this in the next class. Okay.